Yes, good morning. So in previous class, we have seen what is latch, that to RS latch, what is its functionality, truth table, and how to write VHDL program for the RS latch. And also we have seen a controlled RS latch and its corresponding VHDL program. Now I would like to discuss about the flip-flops. So what is flip-flop? So flip-flop also a latch, but the type of controlling is edge, also known as edge triggering. Edge triggering latch is referred as the flip-flop. Okay, so if the control signal is level triggered, if the control signal is a level triggered, that is in latch case. But if you use edge triggering technique, if you apply the edge triggering, then it is known as the flip-flop. So simply flip-flop means edge triggered latch. Edge triggered latch. So since in previous class we discussed about the RS model, that is in case of latch. Now I would like to discuss about D. Here D flip-flop. I am directly taking the D flip-flop. So edge triggering means the circuit is response to either to rising edge or falling edge. Okay, rising edge or falling edge. That means rising edge means changing the value from logic 0 to logic 1. Negative edge triggering means changing the level from high level to low level. That particular instant only the flip-flop can show the output, otherwise nothing. Okay, so this is the D flip-flop circuit. Okay, so the edge triggering model flip-flop can be designed using two D latches like this, two D latches like this, two controlled D latches, and the clock signal is applied like this, so that it work the total circuit work as a edge triggered network, that is finally called as a flip-flop. Okay, so for D flip-flop the symbol is like this. Now this is the D flip-flop, this is the symbol. It has one data input D and another one is clock input. Okay, so since the arrow is represented like this, it is a positive edge triggered D flip-flop, and two outputs Q and Q bar. Okay, and you know the characteristic table or functional table of D flip-flop as when D is 0, the next state of or the Q output is 0. If it is 1, output is 1. Okay, the next state. Okay. Like that you can take the D flip-flop circuit diagram, functionality and symbol. Similarly, with reference to this, here I am going to represent VHDL program for this D flip-flop. So as usual, you know, first of all you have to write the library IEEE, followed by use IEEE.standardlogic 1164.all. Then entity declaration, unit entity declaration as entity, name of the entity D flip-flop is, okay, it is a user defined name. Then port, what are the different inputs and outputs? Based on the symbol itself you can know, those are Q, clock, clear. Okay, clear actually not shown here, clear in this case not shown. Okay, just take the clock signal, clock Q and Qn. Okay, so Q is only in out, Qn also in out you can write. Okay, based on the programming style, these two are mentioned here, which one is in out and which one is out, and D flip-flop. Then coming to architecture body, architecture name of D flip-flop is, so architecture name here is behavioral, that means the representation is in the behavioral model, so the process statement is used. So architecture begin, then process of CLK, so clock signal is we are using basically when based on the clock signal only the execution of the process can be dependent. Then begin. Okay, so here since clear also they have used, that's why first of all they have checked clear signal. Actually clear is asynchronous input to the D flip-flop, asynchronous input to the flip-flops. Actually that I have not shown in the diagram. But suppose if it is there, actually preset and clear, two inputs generally available as asynchronous inputs. Okay, asynchronous inputs means they can't align with the clock signal. Okay, so first priority you have to give to the asynchronous signals. So first you have to check the clear input. If clear is 1, then Q is 0. That is the flip-flop goes to the reset mode. Suppose if clear is 0, then it checks the clock signal. If proper clock is available, then it do the flip-flop functionality, otherwise nothing. Okay, so see here program. So first it checks the clear signal. If clear is 1, then what is the meaning of clear is 1? The flip-flop expected state is reset state. Okay, suppose if clear is 0, then it checks the clock signal. So what type of flip-flop it is? Positive edge triggering. That's why here the statement is rising edge of the clock. Okay, that is the meaning for the positive edge triggering. Then if proper instant is available, Q equal to D. Since the output equal to input in case of D flip-flop, so Q equal to D. And if end process, and Qn is always the negation of Q. That's why Qn is not Q. Qn is the not of Q. And finally end behavioral statement. Okay, so in case of this D flip-flop with asynchronous inputs, this is the programming style. Okay, next what is next topic here? Okay, JK flip-flop also available here. JK flip-flop having two inputs, J input and K input, and only next state is represented here, that is Q. Actually it also has two outputs, Q bar, and from the previous subject knowledge, that is DELT, we can see the truth table of JK. So if both JK are 0, 0, the expected state is previous state. If it is 0, 1, that is J0, K1, the expected state is reset. Why? Because remember J is similar to S, that is set, whereas K is similar to R, that means reset. Now K value is 1. K value is 1 means the expected state is reset state. Hence the Q n of n plus 1, Q of n plus 1, that is next state of the flip-flop is 0. In case of 1, 0, that is, what is J I said? It is equal to the S, that means set. So expected output state is set state. Hence Q of n plus 1 is 1. Suppose if both are 1, 1, J is 1, K is 1. In case of RS latch, what is the expected state? Undefined, right? Now, but here what is the state here means toggling. Okay, continuously it toggles. Toggling means changes its states as set, reset, set, reset, like that. Suppose initially if it is set, it comes to reset, or initially it is reset, it comes to set state. Okay, so like that it change the state. Okay, so then so for this I think you have already studied in DELT subject about the JK flip-flop. That's why I am not going to discuss detailed operation of about this JK flip-flop. Just I am showing how the truth table of JK flip-flop will be appeared. Okay, so based on this I am going to write the program. So for in case of program, as usual, library IEEE, use IEEE.standardlogic1164.all as a beginning statements. Then coming to entity declaration includes all input ports and output ports. Here different input ports are J, K, clock. Of course clear is asynchronous input. Q, Qn are the outputs. Okay. All inputs and outputs ports are declared. Then coming to architecture body, here also it is written in the behavioral model, and here one declaration taken as JK, its name is signal JK, standard logic vector of 1 down to 0. Okay, for JK is one signal declared as an array consisting two locations, JK of 1, JK of 0. So on declaration here use, then begin, after begin process of clock signal. Okay, process of clock, then begin, process begin. So the variable JK value is J ampersand K. J ampersand K means concatenation operator. Ampersand is actually concatenation operation. So whatever the value of J and whatever the value of K, they should be placed in side by side. Okay, so let us see what will happen, how they have taken like this. First of all, the asynchronous input you have to check out. If clear is 1, then the expected state is reset state. Therefore, Q is assigned with the value of 0. Okay. Else means the clear value is 0. If clear is 0, then you have to check the clock signal. That too in place of clock, which one, positive edge or negative edge? Assumption here is positive edge. So rising edge of the clock. Then checking the JK value as case JK is case. Here case statement is used for checking JK values. So if JK value is 0, 1, if JK value is 0 means J is 0, K is 1. K 1 means expected state is reset. So Q equal to 0. When 1 0 means J is 1, K is 0. So set state we are expecting. So Q equal to 1. In case of 1 1, toggling action. Toggling means suppose previously if it is in set, now you can expect to set reset state, or previously if it is in reset, expecting state is set. So Q equal to not of Q. Okay. When others, null, nothing, don't do anything. That means it is as per the syntax you have to write the when others in the case statement. Then finally end case, end if, end process. So up to this the flip-flop action is over, but you also has to mention the Qn value, that is Qn is always complement of the Q. So Qn less than equal to not of Q. Finally after that end behavioral, that is end architecture name. Okay, so I think you can clear about writing the VHDL program for this JK flip-flop. Okay. Then you check it once. Okay. After that we have the T flip-flop here. In case of T flip-flop, if the input is 0, no change will occur. Suppose if the input is 1, the toggling action you can observe in case of T flip-flop. Toggling means suppose in the previous state is set, now the expected state is reset. Suppose if already the state is reset, now expected state is the set state. Okay, so such a action we can observe in T flip-flop case. Here the program is there, but you try to write the program for the T flip-flop. And in the next class, I would like to discuss about the register. Okay, register. Okay, now I would like to stop here.